Good evening, everyone. On behalf of RISE Lab, I welcome you all to the seminar on sonomyography towards intuitive bionic control, organized by the Center for Biomedical Engineering, IIT Delhi. We have our esteemed guests, Professor Siddhartha Sikdar and Shriniwas Patwardhan from George Mason University, USA. It is my pleasure to introduce our first speaker, Professor Siddhartha Sikdar, who is currently a professor in the Department of Bioengineering at George Mason University. He is also the director of the Center for Adaptive Systems of Brain-Body Interactions, CASBBI. His research group within CASBBI conducts translational research using imaging to investigate brain-body interactions for clinical populations such as stroke, spinal cord injury subjects, and amputees. The group is currently investigating the novel use of wearable ultrasound sensors for sensing muscle activity and controlling external devices such as multi-articulated prosthetic hands and exoskeletons. Professor Sikdar earned his PhD in electrical engineering from the University of Washington. He received a postdoctoral fellowship from the American Heart Institution. He has been a recipient of the NSF Career Award, the Volcano School of Engineering Rising Star Award, Mason's Emerging Researcher Scholar Creator Award, and was nominated for the Rising Star Faculty Award of the State Council of Higher Education in Virginia. I would like to invite Professor Sikdar to deliver the talk on sonomyography for control of upper limb prosthesis, current state and future direction. Please welcome.
Thank you, Aisha, for that introduction, and thank you all for inviting us to be here today. It's really a special occasion for me. I did my BTech at the IIT Kanpur, so IITs have a special place in my heart, and it's really great to be back here to see how well Bishop is doing in setting up a number of very exciting research projects, and it was great to meet all the students here as well. So I wanted to first tell you a little bit about Mason. I don't think, and make sure I can advance the slides. Oh, not advancing over there. Oh, great, thank you. Perfect. So many of you may not have heard of George Mason University. It is actually a very large university in the Commonwealth of Virginia. We are in the DC metro area. It is extremely diverse. It's one of the most diverse research universities in Virginia, also in the US. We are an R1 research university, and I joined Mason in 2008. And so even in the last sort of decade or so, it has really grown tremendously in terms of both research capacity, but also in terms of the kind of transdisciplinary educational programs that we are creating there. So as Aisha introduced, I am a faculty in the Bioengineering department, but I also run a university-level transdisciplinary center. And so the CASBBI, or the Center for Adaptive Systems of Brain-Body Interactions, was founded to be a university-level center to really address big challenges that cannot be handled within disciplines, similar to the CBME that you guys have. So we have faculty from many different disciplines across campus. So we have psychologists, social workers, policy faculty, engineers, physicists, philosophers, mathematicians, all working together. And we are trying to address some grand challenge problems at the intersection of health, society, and technology. So some of the problems that some of the questions we are asking, for example, are, how can we ensure that individuals with disabilities can fully participate in life roles and activities? How can we alleviate the burden of chronic pain, which is one of the leading causes of disability worldwide? How can we address substance use disorders? And as many of you know, the opioid use crisis is a major problem in the US. How can we develop better technology-based solutions to help people stay in recovery, especially people who have substance use disorders? So these are some of the projects that we are working on. So we also not only are trying to build capacity for this kind of transdisciplinary research, but also we are very interested in translating this research to practice. So I think, as Bishop was saying, this is one of the emphasis at CBME as well. So that's a similar emphasis at our center. The other big aspect of our center is training the next generation of students. So we have a interdisciplinary research traineeship program where, again, we take students from all over campus. So computer scientists working with social workers, working with neuroscience majors for a year on community engaged projects. So they go out into the community and really involve community partners from the very beginning in formulating the research questions and address problems that are of importance to the community. So this is something that we are, again, very proud of. I won't have time to talk too much about this today, but I just wanted to briefly mention that. At CASBBI, our research portfolio sort of falls into 3 buckets. So we are interested in neuromusculoskeletal function at different levels. So in my group, we are doing a lot of work with amputation. We have other faculty in our center who work on stroke and spinal cord injury. We have a major effort on chronic pain that I'm going to briefly talk about, and then another major effort on musculoskeletal injury and trying to understand both how to better monitor recovery following musculoskeletal injury and also to come up with innovative interventions for preventing injury and return to duty afterwards. Then another major area of focus is brain and behavior. And I know several of you are interested in problems like Parkinson's disease, cognitive function, mobility, and so forth. We have a number of faculty working on social neuroscience, eating disorders, and so forth. And then the last bucket is mental health and addiction. And this is where we are interested in opioid use disorders. How can we not only use traditional interventions, but also technology-based interventions? So using AR, VR, XR kind of interventions to come up with novel ways of monitoring ecologically valid neuropsychological cues, and also come up with non-pharmacological interventions for maintaining recovery and preventing a relapse. So these are some of the areas of work. And again, so the faculty come from many different departments. We have philosophers who are interested in sort of the history of living systems, and they're interested in how our ways of talking about biology is very much a reductionist view when we talk about the cell as a machine, rather than really thinking more biologically, and how that sort of prevents us from asking the right kind of questions. So these are some faculty in our center thinking of those kind of problems. We have a number of people who are doing neuroscience and neuroimaging. So we have neuroimaging, neuromodulation, and then a number of practitioners, so clinicians, as well as social workers and policy faculty, as well as, of course, engineers like myself. So I'll very briefly give a couple of examples of the types of projects that we're doing, and then we're going to talk about the prosthetic control project that is one of the main areas of focus in my lab. So this is a project that I've been involved in for many years, but more recently we have a new major initiative on. And so the idea of this project is that chronic pain, as many of you know, is the main cause of disability. Often chronic pain can be in the neck muscles or in the low back. And for example, almost 80% of low back pain is considered non-specific. That means there's not a clear identifiable cause for the low back pain. And similarly for neck pain and shoulder pain as well. And when the cause of the pain is not known, the treatments are often non-specific, and very often they're not very effective. So there is a great need to better understand sort of the pathophysiology of these kind of myofascial pain syndromes, where there's not an obvious nerve impingement or an injury that you can find on radiological imaging. So we are very interested in studying the pathology in muscle as well as connective tissue, the nerves and the blood vessels, and so in the milieu of muscle. and how that might be altered in some of these chronic pain syndromes. So one of the findings is that the connective tissue actually performs a pretty major role in lubricating the muscle and allowing the muscle fibers to glide past each other when we do muscle contractions. And so in some conditions, the fascia, the connective tissue, may lose its lubricating properties. So it might get densified, and the hyaluronan that serves as a lubricant can aggregate, and that causes a significant downstream sort of cascade effects, and that could lead to various secondary issues. There's also this concept of neurogenic inflammation. So inflammation that occurs secondary to central sensitization in the spinal cord because of some other injury. And so the central sensitization, which is a common finding in chronic pain syndromes, can lead to the secondary neurogenic inflammation, and that could be play a role in all these syndromes. So what we are doing is using imaging as well as high-density electromyography and bioimpedance spectroscopy to sort of characterize the local milieu of the muscle, and then try to come up with a composite biomarker for these myofascial pain syndromes. So this is a project that has been going on for a long time in my lab, but now there's a renewed emphasis on doing a randomized clinical trial with different interventions, as well as coming up with a composite biomarker. So my training through my PhD and postdoc is in ultrasound. So a lot of the work that I do is related to ultrasound. So this other project is, again, something that has been percolating for a few years, but now has gained renewed momentum in my lab, where we are trying to develop a wearable ultrasound patch. Ultrasound, as many of you know, is getting increasingly miniaturized. Commercially, there are systems that are quite miniaturized. We saw several examples of systems in Bishop's lab that are very compact miniaturized systems. But there's a need to miniaturize that even more so that we can use it for dynamic studies. So for example, looking at muscle function while somebody is walking or running, especially if you are interested in musculoskeletal injury and recovery, trying to understand how the muscle recovers following injury. So this is an ongoing project. We are trying to develop new ways of doing ultrasound imaging using frequency domain methods, and that allows us to significantly miniaturize this technology. And so that's an ongoing area of focus in my lab. So those are just a brief introduction to a couple of different projects. I don't have time to go into many other exciting projects that are going on. So I'll switch gears a little bit and talk a little bit about prosthetic control. I know that's a great interest to a number of people in the audience here. So I'll, oops. It's okay. I think that might be okay. So as many of you know, there are many different types of prosthetic technology that are currently available. Many people still use body-powered prostheses, which are essentially not powered. They don't have batteries. They're just operated by cables that are connected to the shoulder or the back. And many people actually really like them. They are quite reliable and intuitive to use. But they don't, in terms of fine manipulation, they could be somewhat limiting. And there could be a lot of other secondary problems that might be associated with this, using these kind of devices. More recently, since about 50 years ago, people have started to use powered systems. So for example, these electrical terminal devices, which are essentially hooks, sometimes with a wrist, that are often controlled by electromyography. So these are electromyography sensors that are placed on the residual limb, and they're sensing the electrical activity of the muscles, and they can be used for controlling opening and closing the hook or rotating the wrist. So these are, again, very popular as a prosthetic solution. Many people use them, and they're quite happy with them, but they do not have the kind of fine dexterity for doing multiple fine movements. So there's been a push in the last decade or so towards more multi-articulated hands that many of you are probably very familiar with. These are hands that have individually controllable fingers, and they are capable of many different types of grips. The challenge is how do you control these different degrees of freedom? So that has been an ongoing problem. There have been some solutions that are quite successful. Pattern recognition is now commercially available. I'm delighted to see our collaborator Damini, who works for Infinite Biomedical Technologies. We are collaborating with Damini's company. Damini, their company makes a pattern recognition system, one of the two that are commercially available. So pattern recognition uses a number of EMG sensors and then uses a machine learning algorithm to try to infer what the intent of the user is. And it works quite well, but it has several drawbacks. It takes a long time to train these users to do these kind of tasks. Many users cannot reliably use more than 2 degrees of freedom. Sometimes controlling 3 degrees of freedom could be a challenge. So even though there are solutions, it's still not quite perfect. So the research community has been going more towards more invasive solutions. So it's things like targeted muscle reinnervation or implanted electromyography sensors, RPNIs, which are residual peripheral nerve interfaces and so forth. So these are more invasive solutions that could be better suited than pattern recognition, but then they require an invasive surgery. So I wanted to take a step back and say that, prosthetic devices have been around for a very long time. And if you look at some of the devices that are currently available, they don't look all that different from what what was there in the Roman times or in the 1500s. In terms of the design, obviously now we have electrical motors and so forth. But in terms of functionality, I don't know whether we have come all that much. We have certainly come quite a ways, but there's a long way to go. So the other point I wanted to make is that, as engineers, we tend to think that more sophisticated devices are always better, but that may not be true. Many users would much rather use a body-powered prosthesis than a multi-articulated hand. So in the literature, oftentimes people talk about device abandonment, where people would not use a sophisticated multi-articulated hand because it's just not functional for what they would like to do. They're much more functional without a terminal device or with a body-powered device or with a ETD. So there are pros and cons of each one of these systems, and these have to be personalized. So each person may have a different need or desire for function that the technology may or may not solve. So that's an important point. So here's an example of a quote from one of the user magazines that says that this person says that they have the most sophisticated hand in the limb in the market, and they really hate it. It really doesn't do much for them. So the other point I want to make, and this is primarily for the students, and again, when we think of as engineers, we think that creating this sophisticated functional prosthesis is the solution to the problem, but actually it is not. The ultimate goal is not just the prosthetic device. The ultimate goal is to improve participation in activities of daily living. That's the goal of rehabilitation. And that goal, in part, can be solved by technology, which is replacing the lost function with a prosthetic device. But that's only one part of this whole biopsychosocial model, which is part of this international classification of function. And you can see that there are many other domains that really need to be addressed before a device truly becomes functional. So I just wanted to make that point for the students, especially as you're thinking about developing technology. Do not forget that the ultimate goal is not the device. It's really, you want to improve participation for the users. And at the bottom, I put the sort of a typical sort of care continuum for what a user goes through when they have an amputation and get a prosthetic device. And it's a pretty complicated and long care continuum. And developing the technology is only one small piece of this. So there are many other dimensions to it that we really need to think about as well. So this is the kind of sort of transdisciplinary, interdisciplinary thinking that we are trying to cultivate in our center, and I think that you guys are doing it at your center as well. So I just wanted to emphasize that. With that, I want to talk a little bit about the technology piece of it. So just to give you a sense of why we think that EMG may have some challenges. So here's an example of ultrasound images, cross-sectional ultrasound images of the forearm. It's an able-bodied subject trying to do an index finger flexion and a middle finger flexion. And so to orient you, some of you are familiar with ultrasound, others may not be. So this is a cross-section through the forearm. You can see the bone at the bottom, and then you can see that there's these different muscle compartments. There's the flexor digitorum superficialis, which is at the top, and the flexor digitorum profundus, which is at the bottom. And as you flex the index finger, there's a portion of the FDS muscle that gets activated. As you flex the middle finger, there's a different portion of that muscle that it's activated. It's even more complicated. Each individual joints of your finger actually are controlled by two completely separate muscle groups. So the FDS controls the more proximal joints, the FDP controls the more distal joints. So there's a lot of complexity in the musculature that needs to be captured if you want to isolate index finger flexion from a middle finger flexion. And electromyography sensitive to superficial muscle fibers because it's a surface electromyography system. So you're sensing electrical currents from the surface of the skin. So these deeper layers of muscle that are getting activated may not be picked up by the EMG sensor. Even if they're picked up, it's very hard to differentiate between these overlying muscles. So that's one of the big challenges in isolating these individual digits. So, so in terms of the challenges, I think I may have lost my slide is no longer advancing. I think we are in holding mode.
Oh, Windows is doing something funny. We have the presentation, right?
Sorry about that. Yeah. You can go straight to
just this one.
Okay. I think it's okay.
Yeah.
From the Okay. Okay. Thank you. So yeah, so as I was saying, obtaining control signals can be challenging with electromyography, especially when we are talking about deep-seated muscles. So pattern rec is one technique that tries to overcome this with multiple EMG sensors. But as I was mentioning, there are other more invasive methods that people are pursuing to overcome this. Now, not every patient is willing to try an invasive approach. There's a paper by my former postdoc, Susanna Engdahl, that shows that there's a significant portion of the population that may not be willing to undergo an invasive procedure to get this added function. So in our lab, we were one of the groups that started investigating this idea of sonomyography. So with ultrasound, as you saw, we could very clearly see all these different layers of muscles. So can we use ultrasound itself as a control signal? And I know you, many of you are well familiar with this because of Bishwar's work here as well. But this is an approach that we have been investigating, and a couple of other groups in the world have also been investigating this. So the idea is that you have these ultrasound image sequences, and over time you get these patterns of activation, and then can we then use a machine learning algorithm to extract these patterns of activation to form a control signal. So for those of you who are not familiar with this technology, this is somewhat different from electromyography in that instead of looking at just temporal features, we are looking at both spatial and temporal features, so spatial-temporal processing. So here's an example of how this might work. So this is an example of somebody doing a real functional test. So this is a I'm going to actually show the task first and then show the data. So this is one of our subjects. They are actually controlling this task, a prosthetic hand, which is a multi-articulated hand, with an ultrasound-based controller. So there is an ultrasound sensor in the socket of the subject, and so we are sensing these ultrasound signals in real time and controlling the hand. And so she's doing this task of that's uses a large workspace. And the reason we're using this task is because one of the big challenges is when you move your arm, there could be changes not only in the morphology of the muscles, but also potentially contact and so forth. So this is a big challenge with EMG. Is also potentially a big challenge with ultrasound, but we have developed some training algorithms that allow us to overcome this. So this shows the outcome over 3 different tasks, the box and blocks task, a targeted box and blocks task, and this customized rainbow task that we developed. And it shows that over 3 hours, the performance was relatively stable. So this was repeated performance of this task for over 3 hours, and it seems to be pretty stable. We also show that we can get stable classification over time in a number of amputee subjects. So this is a paper with 8 subjects where we showed that they were able to get close to above 90% classification accuracy on the very first try. On the very first time they tried this system, they were able to get a high classification accuracy, which is very important because it allows prosthetists to then make a decision whether somebody is suitable for getting this kind of multi-articulated hand or not, whether they're capable of these multiple degrees of freedom. As I mentioned, there's a long care continuum. So making this decision quickly allows this care continuum to be somewhat shortened, especially from the pre-prosthetic training perspective. So we have been developing this technology a little bit. So we now have these single element transducers where we can have very miniaturized electronics. And so we can get similar sort of spatiotemporal patterns when somebody is doing different types of grasps using just a 4-channel system. And we have shown that this can lead to similar classification performance as our full field clinical imaging system. So I put the references at the bottom. If you're interested, you can take a look at these references, and I'm happy to talk more about this as well. So right now, where we are with this technology is that we are about to start our randomized clinical trial. So our technology is to a point where we are ready to put it inside a socket and have subjects do functional tasks. Let this video play. And so we are going to do a randomized clinical trial of myoelectric control versus this SMG-based control. And the types of outcome measures we're going to use are, of course, standard clinical outcome measures, but also biomechanical measures and gaze tracking measures. And the reason is because here's an example of the same subject using myoelectric control on the left and sonomyography on the right. And they're using this box and blocks task where they're supposed to move these blocks across from one part of the box to the other. And you can see that with myoelectric control, they start out really well, but over time, their ability to manipulate these blocks goes down. And they're using a number of compensatory movements. So they are using a lot of their trunk movements to compensate because they don't have fine control of the terminal device. And whereas with the SMG, they seem to be standing up more straighter. And so we want to quantify this. So we have been collaborating with Dr. Jackie Ebert at the University of Alberta, where she has developed these gaze and motion tracking metrics. So we think that using these more sophisticated metrics are going to be important when we are trying to show differences in fine control, rather than just look at how many blocks can you transport over a given period of time. So that's this is the ongoing work. So here's the summary. So we think that SMG could become a clinically viable solution relatively soon. I think we are getting close to a point where we can start thinking about the clinical use cases. The potential is really greater flexibility in selecting the optimal treatment plan for each subject. So as I mentioned, not everybody needs a multi-articulated hand. Sometimes they need just more proportional control with an electrical terminal device. And so the ability of SMG to give better proportional control may be a pretty compelling argument for that particular patient. Or there could be other use cases that we still have to find. So the point is that it's not a one size fits all. We think that there are some issues with deep musculature that EMG just cannot access because of that SMG can. So that's one obvious advantage. Srinivas is going to give a talk on proportional control. So you'll see the ability to do proportional control with SMG. And the other issue is with many of these subjects, they have residual neuromuscular damage and also scar tissues and so forth. And so that could be an impediment for electromyography signal acquisition. So we think that SMG might be able to overcome some of these things. So with that, I'm going to hand it over to Srinivas, who is about to finish his PhD. And he has done some really nice work on using SMG for proportional control. So Srinivas. Or we could also do questions at the end if you want. I'm happy to answer questions if you have any right now.
Thank you, Professor Sikdar, for your insightful talk. Now it is time to welcome Shriniwas Patwardhan, who is a PhD candidate in the Department of Bioengineering at George Mason University. His research has been focused on quantifying the relative contributions of visual, haptic, and other feedback modalities for prosthetic limbs. He was a fellow in the National Science Foundation's Research Traineeship Program at CASBBI, where he worked in an interdisciplinary team to devise solutions to improve data-rich communication between persons with Parkinson's. He has presented his work at several international technical conferences such as ICOR, SFN, and EMBC. He did his master's in electrical and computer engineering from the University of California with Professor Jon Wiesel. He is the winner of Mason 3-minute thesis at Mason University. Also, he was the Arise Fellow in the US FDA. The topic of his talk is on the role of multisensory feedback during prosthetic control. Please welcome Srinivas Patwardhan.
Get a feedback.
Can you hear me?
Yes.
So, hi, I'm Srinivas, and I'm a PhD candidate in Dr. Sikdar's lab. So that's where I met Bishwaroop, and
The presenter view. Maybe you can just the turn off presenter view. Right, show. Turn off presenter.
right. So actually,
You need the presenter.
no, I just want to see the presentation. So right now it's in my view. Okay. No, I just want the presentation.
It is already in the presentation. Right? Oh, hold on. Oops. Primary monitor has changed. Now it's showing the presenter view again. Hold on. What's it? So it's screen capturing this. It should screen capture that. So we can stop the screen share here. And start the screen share.
Maybe first present, then
Yes. And now if you do it, How about now? Yeah.
All right. So it's a law of demos, right? It everything is tried 1,000 times and it always goes wrong during the presentation. So anyway, so I'm going to talk a little bit about proportional control and what we've been doing using sonomyography for proportional prosthetic control and maybe applications beyond just using it for prosthetic control. But to orient everyone before that, so using your hands is a multisensory experience. So you use your eyes, your sense of touch, even your ears, and your internal model of what you're exactly doing with your hands. So it's so to try to make the point, what I'll say is, imagine waking up in the morning and trying to look for your phone. That's usually the first thing all of us do. And it's not a simple task if you don't have any sensory feedback at all. So you imagine your hand being numb, you've slept on it all your night, right? And it's not a pleasant feeling. You're going to fumble around a lot without any of these sensory, without any of the sensory information. When it comes to prosthetic hands, it's not that different. So using a prosthetic is also a multisensory experience. Unfortunately, most of the commercial devices and even a lot of the research devices that are made today do not make use of all of the sensory input. Now, either they don't make use of all the sensory input or the user has to rely heavily on one input or the other. So traditionally, because they have no haptic feedback and the users are using very ad hoc mechanisms to actually control the limb, the touch and the internal model is kind of thrown out of the picture, and the users rely heavily on being able to see what the hand is doing in order to make sense of their motor actions. So back in the 70s, this was a general model proposed by Childress, I think it was like 1973. And this is sort of the feedback loop that he proposed generally, not just for prosthetic devices, but more broadly for sort of human-computer interaction type of applications, where you have the central nervous system and the sensory motor system in a two-way communication with each other. Then they are talking to some type of controller. In our case, that's the prosthetic sort of pattern recognition system or sonomyography or whatever that is. But it may be any other HCI through which you're communicating with the computer. And then there's the final plant. So in our case, again, is the prosthetic hand. It may be something else. And finally, that plant is what interacts with the environment. So you may be picking up a cup or doing something with your prosthetic, and that creates feedback. So there may be tactile feedback, visual feedback, auditory feedback, and so on. That feedback is fed back in one way or another. So some part of it might be going directly to the central nervous system. Some of it goes through the sensory nervous system back to the brain. Some of it might be going just back to the controller. And unfortunately, a lot of these loops are not closed when users actually do prosthetic control tasks. So typically, it's just the eyes. There's only one feedback loop going back, and the users have to look at what they're doing with their hand to make sense of what is happening in their environment. And that's not the best way to use their hands, because that feedback is there. We just have to construct prosthetic devices and control algorithms in a way that they actually make use of all of these feedback loops properly. So what we did in our lab is, so I'll talk a little bit about that later. First, I have two videos here. I think you saw the video on the right before when Dr. Sikdar spoke. The video on the left is similarly a person using my electric prosthetic. Both of these are very experienced users. And you can see they have quite a bit of challenge trying to do very basic tasks. So on the left, he's trying to do a clothespin allocation task where you pick up the clothespins from the horizontal bar on the bottom. You then move your wrist and place it on the top. On the right, it's a box and blocks task. Now, apart from just control problems that Dr. Sikdar talked about, there are also sensory problems here. So they cannot tell just by not looking at the hand whether they have touched the object or not. They have to be looking at the interaction. So that's one problem, because they cannot do something else while they are doing this. And typically, the way you test that is by doing dual task or multitask paradigms, where you ask the subject to do something else while they are doing that task, and the performance drops quite drastically. But in our lab, what we have been doing is using sonomyography. So just a brief saying, sonomyography. In sonomyography, typically we ask if we have the users doing these multiple postures of the hand, each of them will have an associated ultrasound cross-sectional image that can be pumped through our machine learning algorithm. I'm not going to go into details about what we exactly do, but I'm happy to answer questions later. But that then be used to actually generate a proportional signal that is tied directly to the joint kinematics. So in this case, to the joint angle. So from full extension to full flexion, we are able to generate a value of 0 to 1, and then that can be fed to some kind of an HCI. So here you see a wrist flexion extension. On the x-axis, you have the measured motion completion level. So this is the ground truth that we measured using leap motion. Not my favorite device. I would have done something better, but it is what it is. On the y-axis, we have the derived proportional signal. So the fact that these signals are quite linear means that we are actually predicting the joint kinematics quite well. And not just for this, we are able to do this for a power grasp, that's a hand open close, and a wrist adduction abduction as well. And just examples. So on the right, you saw that video before. On the left, what you see is the user actually using proportional control. So what you should, wait, let me actually pause this video. So the important part here is this is not just on-off control. It's not just making the hand go to the end motion state or 0. It's going to partial states, which is important because you just don't want to pick up the same cup every day. You want to be able to pick up cups of different size. You want to be able to do different things with your hand, right? Where you'll see this, the great benefit of this is the user will pick up that bottle. There's water inside the bottle, so it's a squeezable bottle. It's plastic. And he's using proportional control to actually squeeze the bottle harder such that the water level rises, but not so much that it spills out. So he does have fine motor control over how much he's squeezing. And then he makes the water level go down and he keeps the bottle down again. Okay. So see, you pick it up and then there you go. But he could stop the squeezing exactly as the water level was about to go too high. Then come down again. And that is Vishwaroop. So, the interesting thing here is we did not ask the subject to do this. We just asked him to play around with the bottle while we were taking the video. He felt comfortable enough within a few minutes of being able to use the system to do this. Now, that's promising. Okay. So in a sense, we use sonomyography to decode motor intent. So that is what I was just talking about. But then it's what I personally am interested in is investigating the relative effects of providing multisensory feedback. So now can we use sonomyography as the control input to an HCI to actually test how those feedback loops interact with each other? So can we deprive the user sort of systematically of different types of feedback and measure the relative effects of depriving them on their performance? So for this, we designed a 1D virtual cursor control task driven using sonomyography, again, using Vishwaroop's figure. So what happens here is you can see there's a sonomyography probe there's an ultrasound transducer that's imaging the forearm in real time. That is fed to a computer. Our algorithm generates a proportional signal, and that is then sent to this blue cursor that goes up or down based on the level of flexion. So if the user flexes their muscles more, the cursor goes up. If they relax their muscles, the cursor goes down. And the task is essentially this red line is presented at different targets on the screen, the different heights, and they have to meet those targets using the appropriate flexion level. And this is done using all different kinds of motion. So you can have like a power grasp, which is hand open close, wrist pronation, thumb flexion, index flexion, and so on. So in our earlier work, what we did is these are different motions, and the x-axis in each plot is time. So as time progresses, the blue traces the user performance. So different targets are presented that are those black lines with the small green dots. And as the new target is presented, the user is able to immediately switch to the new target just by manipulating the level of the extent of flexion in their forearm muscles. And this was quite promising because this we did with 5 amputee subjects and I believe 3 amputee subjects, and all of them were able to actually perform up at least 3 motions. So that was sort of the first foray into this. But then, like I said, can you isolate different feedback modalities and measure their relative effects? So that's what we're going to look at. So in the first part, we deprive them of complete visual feedback. Now, it's known that when you're actually reaching for objects in space using your hands, there are errors when you're using just your sense of proprioception. So if you close your eyes and ask yourself to touch the same object that you just touched, you'll actually end up touching different points. And this is known for like gross body level movements. But what we tried to do is, can you measure that same effect in an internal measurement done using sonomyography? So for that, we designed a standard task. I'm sure a lot of you are familiar with it. So again, we put the hand inside an opaque enclosure so the user does not have visual access to their hand. The more they flex their hand, the cursor goes up and so on. And this would be somewhat of a sample time trace. So as time increases, they will first try to acquire that red line. They might shoot up, then try to sort of re-stabilize, go down, and eventually stabilize at the target. Now, this is a sample time trace. This is not exactly how it works, and I'll show you some examples later. So what we found is, over here, you have a 30-second time window where we gave them visual feedback, and they were asked to acquire a certain target. So they're quite accurate. So once a target is shown, that's the horizontal dotted line, the subjects were able to acquire the target quite quickly. And then once the hold phase was initiated, they still had visual feedback. So they just kept on holding onto the target. But in the next phase, we actually deprived them of visual feedback in that second phase. So they used visual feedback to acquire a target, and then they were made completely blind. There were some errors in that, but the interesting case is the last one, where we asked them to acquire the target under visual feedback, then go back to rest, and now acquire the same target that they had just acquired, but under completely blind conditions. So essentially, the task would be do a flexion level, remember what it was, go back to rest, and try and do the same flexion level again. Turns out that users are not very good at doing that. Okay. So only proprioception alone is not, it allows for only an approximate level of control, but not fine motor control. So then naturally, I think, oh, okay, yeah, sorry. What we saw is there's very small position errors when they have visual feedback, very large errors when they are doing this blind acquisition. Interestingly, stability error is the same across all. Now, what that means is the users go to the wrong target, but when they go there, they think they are at the right target, okay, because they hold at that target with high confidence. Okay. And that informs some of the stuff that we did later. Then obviously the next question was, how does haptic feedback impact this? So now can you deprive the users of visual feedback, but still get their performance back using haptic feedback? And an example of this would be exactly like I said before. You wake up in the morning and you try to pick up your phone, but you don't want to look at it, right? You're just fiddling around on your bed and you eventually get it. Can you do that in the prosthetic case? So can you allow users to interact with their objects without looking at it? So we developed this haptic band that was made up of small vibrotactile elements that went on the forearm and that vibrated proportionally to the amount of overexerted force or an error between where they had to be and where they actually were. And again, we saw the same thing when they were given visual feedback. They were quite good. Once visual feedback was taken away, there was a large degradation in performance, but that actually went away once haptic feedback was given. So that third violin. So first there was both visual and proprioception, then only proprioception and proprioception plus haptic. Ideally, you would want proprioception plus haptic to perform as well as visual plus proprioception. That would be sort of the gold standard. But other literature, not just prosthetics, has also shown that that is not what will actually happen. Their haptic is good, but not as good as visual. Visual will usually overpower every other sensory modality. And again, there was no relationship between the target level and the error. So there was just a sanity check. Then this is, did somebody say something? Okay, questions. But then this is somewhat more of the exploratory part from here on. So what we wanted to look at is not just sort of these task performance metrics or these end state performance metrics, but more the dynamics of the signal that users generated during these proportional control tasks. And that is sort of more interesting, not just to prosthetic control people, but also largely neuroscientists and motor control experts and so on. So what we did for that is, if you imagine this user trying to move a manipulandum in space, that's just an object that they're holding in their hand, and they're going to move it from point A to point B. This has been a very well characterized task in motor control literature, and there are very typical trajectory curves that users follow when they actually move objects from sort of one point to another. And they're basically the minimum jerk trajectory, where the left is the position versus time, right is the velocity versus time. So you have this sigmoidal shape in the position, and that results in a bell-shaped velocity profile. One interesting thing is that peak of the velocity curve actually scales with respect to movement distance. So if I ask you to move from point A to point B, you would have some peak velocity. If I double the distance you have to move, the height of that bell curve would double. And this has been well documented throughout the motor control literature. This is almost used as a gold standard to sort of check for degradation in performance after people have some type of neurodegenerative or neural problem. But then we said, can we actually do that again using an internal measurement using sonomyography? So we used a similar setup where we instrumented users with ultrasound probe, and we're generating this proportional signal and checking if, or rather investigating if they actually show similar performance in the virtual trajectories generated by sonomyography. Are those similar to the trajectories generated during whole body movement or movement of an entire limb? And that would be an interesting finding. So what we saw is on the top, you see the position curves separated by target distance. So like I said, and the bottom is the velocity curve. So this is when the user is actually moving their limb from one point to another. And as the target distance moves further away, or the more they have to move, the peak velocity increases. Now, this is a standard known result. We did the same using sonomyography. So you see this red line that was the target presented on the screen. The X on the screen is controlled by the user using sonomyography. And we presented the red line at different points. So the task was, you see a red line, you acquire the right level of flexion to actually move your cursor to the red line. And we characterized the trajectories taken by the user in that movement. And what we saw is we see very similar performance. So you see this minimum jerk trajectory in the position and velocity profiles of sonomyographic control as well. Now, this has some implications, because what this tells us, and we're sort of in the process of arguing this out with motor control experts everywhere, is this tells us somewhat that the users are intuitively using this control system, because you see very similar curves between whole body movements that they are doing intuitively and naturally, and trajectories generated from sonomyography. And that seems like a tenuous sort of connection, but we're trying to get there, and that is sort of the approach we're taking from here. But this could also be useful in many other ways. So beyond prosthetic control, if you wanted to characterize the movement done by somebody, so you could use this as a tool to probe the level of degradation. So you could say, an able-bodied subject does a trajectory very, very close to the minimum jerk, but now I have a stroke patient and their minimum jerk is broken down in a very specific way, and you could sort of characterize that. And I think Manikandan, you actually worked on very similar sort of spinal cord injury patients, right? So this is the type of analysis I was talking about. You could actually use your curves to sort of correlate with respect to the minimum jerk. And then another interesting aspect of using sonomyography for that is stroke patients might actually have degradation along multiple levels, so from proximal to distal. And then you could actually characterize the level of degradation at different points as you move from proximal to distal. So you could actually go in and say not just the end trajectory is broken down, but it's broken down in a very specific way. So their elbow is following minimum jerk, but their wrist is not, and their shoulder is not. And then you could target the therapy in that direction. So this could also become another sort of tool in the belt of rehab specialists. So that's sort of the direction we are taking this, and hopefully get there soon. And yeah, so that's all my slides, and those are my collaborators. As you can see, Dr. Mukherjee featured quite heavily in all our work. A lot of it was extension of what he did in our lab as a postdoc. Yeah, thank you for having me, and I'm happy to answer any questions.
So with that, I'd like to conclude the session and thank Professor Sikdar and Srinivas for such a enlightening talk. Thank you for coming down away from the US and sharing your research with us. I'll say this because I was personally involved with multiple projects and for a long time been associated with Professor Sikdar. I want to share how I got into his lab, because I know there are a lot of prospective PhD students who are looking to do postdocs. So when I went to his lab, during the interview process, what he asked me were questions that really showed me that he had an interest in my career more than his own professional development. And that is the true goal of a mentor. And in him, I found that truly dedicated mentor who was willing to invest in my career more than his. So with that, I really want to thank him and his contributions, not just to ultrasound research, but to my professional development as well. So really very.
And I can say that there's nothing more, joyful than coming to visit Vishwarup and seeing how he's thriving. And so all of you guys have a fantastic mentor in Vishwarup, and he's destined for great things. So thank you for everything you're doing. Thank you for, congratulations on your success.
Thank you. And Srinivas is a great friend. And is there something you want to talk? One more question? Okay, why not? Sure. Wait, let me just finish the word. I do want to thank Srinivas. Srinivas is a very, very good friend. He often jokes that, so in my office used to be the place where they would come down sometimes at odd hours, during work times to just chat. And I can tell you honestly that in a lab, the friendship matters more than, and that is where research thrives. A friendly lab is where good research happens. And again, a plug for their lab. It's a wonderful work environment, workplace. So if you're looking for opportunities, please do reach out to them.
And we have positions open.
Yes. Looking for talented people, and IIT is a place where we can supply that. So again, Srinivas has recently accepted an offer from NIH for a postdoc. So congratulations on that too. And we hope to have you back as a postdoc later. Yeah, and with that, we have two mementos to share, and then we can ask it. So I'll invite Dr. Shahid Malik to just hand over the memento to Srinivas. No, there's one that's written SP beginning. Thank you. And I'd like to invite Dr. Amkesh Jain, close friend, collaborator, to hand over the memento to Professor Sikdar. And to conclude, we'll have one last question.